Hello everyone, I'm Zhonghui Huang. Currently, I'm a postdoctoral researcher at the University of Liverpool. For this presentation, I'd like to share some ideas and work from my PhD at the University College London on using AI to automate population pharmacokinetic modeling. When we talk about using AI in a specific field, I believe there are a few questions we naturally focus on. First, is AI-driven modeling as good as a human modeler? Second, how much modular effort can be reduced? Third, how far can AI-driven modeling go? So keep these questions in mind. Let's keep going. Let's start with why POPPK matters. I think FDA guidance already gives us a clear answer. So that is the key purpose is to support dose selection. It helps answer practical questions. For example, should the dosing regimen be once or twice daily? Or do we need dose adjustments for special populations? Therefore, it is a fundamental piece of the submission package before approval. Now, just to take a moment to think about this. For a modeler, how long does it really take to build a POPPK model? Well, the answer is that it usually takes 12 to 26 weeks, roughly 3 to 6 months, especially for a large dataset. The time goes into project setup, data preparation, model development, review, and reporting. Of these, model development usually takes the largest share of the time. That's why we started thinking that if AI can take on some of modeling work, it could free up capacity for both individual modelers and of the team. More specifically, that could bring further benefits. First, lower cost. We don't want our highly trained modelers spending most of their time on trial and error model testing. Second, faster decisions. If modeling moves quicker, programs can move forward sooner. Third, a stronger evidence package. If we spend less time on modeling, we can invest more in interpretation and building a solid submission package. So that is where the Analytics 2 Auto family comes in. The packages are built within the Analytics 2 ecosystem. Analytics 2 itself is a widely used and importantly freely available platform for nonlinear mixed effect modeling. It has more than 61,000 downloads so far. Building on that ecosystem, I developed the Analytics 2 Auto family, which now has two R packages on CRUN, both freely available. The first, Analytics 2 Auto Init, focuses on generating initial parameter estimates. That's a basic but necessary step that often requires manual guessing. The second, Analytics 2 Auto, uses AI search algorithms to automate the selection of appropriate base POPPK model. Until now, the two new packages has been downloaded more than 1,000 times, which has been very encouraging. Next, I would like to briefly explain the basic idea behind how AI search algorithms explore models. Traditionally, a pharmacometrician usually builds a model step by step, starting from a simple model and adding complexity one piece at a time, testing each model feature sequentially. In contrast, the AI search algorithm takes a different approach. It generates a bunch of the models in parallel, looks at how they perform, and then decides what to try next. This allows for a more flexible exploration of the model space using algorithm-driven search. Currently, Analytics 2 Auto includes three AI search algorithms: genetic algorithm, typo search, and undercurrent optimization. Each has its own way of representing a POPPK model. For example, the genetic algorithm echoes the model as a chromosome. Typo search uses a string representation, and the undercurrent optimization treats it as a path. Based on that representation, Each algorithm then uses its own mechanism to iteratively update the model. Of course, one of the first questions we care about is how well do these AI search algorithms actually perform? To evaluate this, we compare the three algorithms with a stepwise modeling algorithm. This stepwise approach is essentially a simplified version of the traditional modeler workflow. And then we created 144 simulated datasets and used exhaustive search to identify the best model for each dataset. This gave us a clear ground truth for benchmarking the different search algorithms. So, the stepwise approach achieved an accuracy of about 60%, meaning that it identified the true model in roughly 60% of cases. So, if that is our baseline, how did the search algorithms perform? On average, they achieved around 90% accuracy, representing an improvement of approximately 20 to 30 percentage points. These results suggest that the search algorithms can explore the model space more effectively than a conventional stepwise strategy. So, what does it look like with the real clinical data? Let me give an example. Here is the concentration time profile from a published study. This study brought the data together from 10 clinical trials with more than 800 subjects and over 4,000 concentration measurements. It includes both race and smart sampling as well. So we use these publicly available datasets, run it through Anomic 2 Auto, and then let this package search for the best base model. Then we compare the model selected by Anomic 2 Auto with the expert model reported in the published paper. The result was very encouraging. Anomic 2 Auto identified the same base model as the experts. So let's come back to our first question. In our test cases, the AI approach clearly performed better than the stepwise algorithm, which was designed to mimic a modeler's workflow to select the base model. On the other hand, its performance was comparable to that of experienced pharmacometricians. You might wonder why. One key reason is that the algorithm follows a fixed process, while human modelers are more flexible. A modeler can look at the published model, previous reports, and the diagnostic plots to make better informed decisions. Next, I will talk about what Anomic 2 Auto actually does for you. From a user point of view, you just need to provide a dataset, and it gives you a best base picking model. Under the hood, it takes care of several key steps. First, the initial parameter estimation using Anomic 2 Auto unit, which handles the necessary starting value step. Then, it runs the model search with AI search algorithms and automatically estimating parameters and evaluating models along the way. We also have a comprehensive model evaluation system that has been intensively tested. Now, let's come back to our second question. How much effort can AI save for modelers? With the AI tools I have built so far, we have merely been tackling the repetitive workflows. So the goal is to take these repetitive tasks of the modeler's place and free up their capacity for work that really requires scientific judgment and expertise. Looking ahead, I can see the modeler's role shifting from the executor to supervisor. In the past, much of our time was spent on modeling and the repetitive tasks. Today, AI tools can automate parts of this workflow, allowing more time for interpretation and decision making. In the future, I believe AI could go further. For example, combining machine learning with the PK to make sense of the data that cannot be explained by PK. The spotting covariates in high-dimensional data and bringing the pharmacogenomic press to suggest mechanistic hypotheses Finally, the modeler will integrate evidence, evaluate the AI-generated insights, and make the final scientific decisions. Finally, let's answer the third question. In my view, AI is a partner, not a replacement for modelers. There are many areas where AI can contribute in the future, but it's not about kicking us out. So it's about taking on more of the heavy, repetitive work, but ultimately, it's still the model who interprets the results and makes the final decision. To conclude, I'd like to leave you with this take-home message. AI can improve both the effectiveness and efficiency of model development. But the most important takeaway is that AI is a modeler's copilot, not a replacement. Human judgment is still essential for interpreting the results and making informed decisions. Thank you for listening.